you were saying that going from this to this was really hard. Do you remember? Then we went from this to this one, right? The one with 4 atoms. Do you remember that? You don't remember that?
Frankly, no. I remember the 3.
You don't remember the 3?
No, I remember the 3.
You don't remember the 4? Well, let's remember 4. Was it this one? Now do you remember?
Yeah.
Now you remember. So, what group was it? There was this group TD, right? You think so? Okay. Now I want to go to infinite chain. So, how we deal with this system that goes to infinity. Okay. Any ideas? So there will be so far we talked about vibrations, right? And there were these translations and vibrations. In an infinite chain, you will have waves, right? So here we reach at the point of waves of particles, right? So let's say these are our particles and they can have waves, right? And waves can have different different wavelengths. Here I have drawn this wave on top of this chain, but what it really means is that for example, if we are talking about a 1D chain, it means that at that particular moment the displacements can be drawn as the following. Does it make sense? So, like, just imagine that positive displacement is like this, and then 0, then negative displacement, etc. So it's like a pressure wave or something. Do you know how the way that sound propagates? Are you following so far? So there is a way to implement this in mathematics, and we will again use e to the alpha concept. Okay, we will again use this one. So you already remember that we were using e to the I omega t, which would correspond to the wave's behavior in time, right? How it oscillates. Do you remember this stuff? Like, let me see if we have it here. Let's go back. Somewhere here. No. But this equation, it had eigenvalues, eigenvectors, and eigenvalues were imaginary. Do you remember that? Okay, I hope you do. So today we will look at the infinite case. And interestingly, when you go to infinity, the system becomes simpler. Like for example, which one seems to be harder, this one or the infinite chain? Or let me make it like this. Like which one is harder, the three atoms with nothing else or an infinite chain? It turns out that this one is hard. This one is simpler to solve. Okay, less number of equations that are. So in this one, how many equations do you need? 3 equations. In this one, let me come to the point. Okay, so basically we are going to use periodic boundary condition. Okay, and we will put just one atom in this periodic boundary, and then we'll repeat it forever, right? But there is a trick. We will multiply each displacement. So let's say this is displacement u, and let's say this is a, the distance between the atoms. We will keep multiplying these with u times e to the I ka, and the next one is u times e to the I 2 k times 2a. So basically, the further you go away from here, you multiply with ka, like e to the I kx. That's what we are using here. So we are basically multiplying the displacement with a wave. Is it clear to everyone so far? Not so much? Let me try to make it more clear. So you know that there is a correspondence between this one and this one, right? So I will try to explain things in terms of sign first. So what is sine kx? It's a wave, right? It's a non-propagating wave. It's at 0, right? What if I write down sine kx minus omega t? After some time delta t, it will move. I know that it will move towards right, and I will show you why I know that. So let's say you have propagated at time delta t and you have come here, right? So what is this point telling you? It's telling you that sine k delta x minus omega delta t has to be 0, right? Which tells you that delta x over delta t, which is the velocity of this wave, is equal to omega over k. Does it make sense? Tell me.
So if it is infinite, how do we decide on x? Is the initial point? How do we choose x to be as a multiple?
That's a good point. So now we will put underneath our chain, right? Let's put our chain. And basically the displacements will be correlated. So this one will be displaced a little bit. This one will be displaced. Okay, let me show you like this. Let's talk about it like this. Does it make sense? Yes? But think of this displacement in the in-plane, like going like this.
It's like a spring.
Yes, it's like a spring. Does it make sense at all? Yes. Okay, let me solve the whole problem and come back to this interpretation, okay? So, I will call this displacement u. This one I will say that it's u times e to the ika. And this one, can you tell me what is this one?
Minus
Exactly. It's minus e to the minus ika. So let's now write down the equation of motion for this particular atom or ball. M times d squared u over dt squared equals to, let's call these spring constants C. Why C? Because we have used already K. Okay. So you have C times this one minus this one, right? U times e to the ika minus u plus C times u times e to the minus ika minus u. Are you following, everyone? So what do you get from here? Hmm? What?
Why are we adding those displacements? Should we subtract them?
Just imagine like this is 2, this is 1, this is 3, okay? So I've just written this one. No, just watch it. Equals to k x3 minus x2, right? Plus k x1 minus x2. It's tricky, I know. You expect that it's x2 minus x1, but x2 always has to be negative because it's Hooke's law. Whenever you stretch it, it has to come back. Thank you. So, how do we solve this equation? Let me make it prettier for you. Md squared u over dt squared equals c times u e to the ika plus e to the minus ika minus 2. Can you make it even simpler? What is this?
2 cosine or half cosine.
2 cosine, right? 2 cosine ka. Do you see that? So then this part is c times 2 times u times cosine ka minus 1. Okay? What is the next step? Do you remember what we were talking about? Actually, it's better if we add something like e to the I omega t here too. Would you be angry at me if I add it right now? No? So what that will bring me is just omega squared here, m omega squared u. Do you see it? Equals 2c u cosine ka minus 1. Do you like this equation?
So now u is a coefficient.
Yes, u is now a coefficient. And for this simple system, just think of one atom. Okay? How many modes do you have? One atom going in one direction only. one mode, right? So do we have translational symmetry? Yes, we do. So there will be only one mode, which corresponds to translation. So you have only one mode. Do you understand this point? But that mode is now enriched by these waves. Okay? You can have only one mode, which is just like u equals 1. So let's finish up with this equation, and we will see something nice. Omega squared apparently is equal to 2c over m cosine Ka minus 1. Right? Do you remember these nice formulas, trigonometric formulas? Cosine x minus 1. Can it be written? Hmm? Yes, yes. Exactly. Anyone here that remembers those relationships? No one?
Yeah.
Okay. Shall I risk? Okay. Let's. No, I don't remember. But something like. Okay, never mind. Something with squared comes out of here. Okay? Let's actually plot it. So I will close these very secret programs. I think this was it. Yes. Basically, I'm plotting x versus square root 1 minus cosine x. Okay, are you ready? Something like this. Okay. So let's try to understand this. Okay. What it tells you. It tells you that as k goes from 0, let's start from 0. What is omega for k equals 0? It is 0. Yes. Because k equals, if you put k equals 0, then you will get 1 minus 1, which is 0, right? For k equals 0, omega is 0. What about Ka equals pi? Mm. Cosine pi is? Minus 1. So you have omega squared equals to minus 4c over m, right? Why you didn't tell me? Sorry. So omega squared equals minus 4cm, which gives me, so I'm going to plot omega here, but that omega corresponds to whatever is left after. For example, this one goes to plus minus I square root 4c over m, right? So I will plot just this part. Is that okay with you? Yes? So whenever I reach pi over a, I have something like this. Have you followed everything so far? Nothing at all?
No, not nothing at all. But not everything.
Not everything. So let's try to understand this curve, okay? So what is k equals to 0? What happens as k goes to 0? Let's draw our sine kx one more time. What is the relationship between lambda and k? Mm-hmm. So
frequency is 1 over time.
exactly. So can you tell again? Tell me. 2 pi over k, or k equals 2 pi over lambda. Everyone agrees with this? Yes? So what happens when k goes to 0? Lambda goes to infinity, right?
Just a straight line.
Hmm?
Just a straight line.
Just a straight line, yes. Let's see what that means for our chain. So lambda goes to infinity means just a straight line. Okay, so I'm going to multiply these. You remember our mode was just 1 and nothing else, and I multiply it with a constant. What do you get? The whole chain moving, translating, right? Will there be any restoring force? No, right? That's why omega has to be 0. Do you remember that when omega was positive, like when we are writing this part, like in the I omega t, when we write omega, okay, when it is positive, there is a restoring force. When it is 0 or negative, for example, when it is negative, it means that the thing actually wants to go that way, right? Are you following, everyone? Very good. Now, if I were to continue this, it would go like this, right? But it would have no meaning. I mean, after this point, there is no meaning in continuing. And can you think of the reason? What happens at k equals pi over a? Let me draw you the thing one more time. So this is a, right? And I'm going to superimpose this wave that has k equals pi over a. What is lambda? 2 pi over k, which gives you what?
A. 2A.
2a, right? So it means that we are talking about the smallest wave, shortest wavelength that you can represent on this crystal. The shorter ones have no meaning. Does it make sense to everyone?
Would they crash?
Hmm?
Would they crash?
No, just this. This is when. Okay, they would not crash for sure. No, they are just not capable of transmitting those waves. I mean, the medium is not physically fit for transmitting shorter wavelengths. Does it make sense? No? Yes? Okay. Let's now solve, or at least write the equation for the system. How much time do I have? Yes, I have some time. For the system that has two kinds of particles, like M2, M1, and it's a chain that continues like this, M1, M2, etc. Do you see what I did there? Yes? So this time you will have some U, some V, some U times e to the IKA, V times e to the IKA, and V times e to the minus IKA, U times e to the minus IKA. And A is this one. Does it make sense to everyone? Yes? So, if I want to write down the equations, how they look like, m1 d squared u over dt squared equals to c times, let's say all force constants are c. Okay? They could have been different, but let's assume. No, they couldn't have been different, right? It's the same bond. Yes, sorry. So, what's the first term? Do you agree with this? Let me write down the second one. Do you agree with this? Everyone? Yes? So again, there are some omegas that I keep forgetting adding, but never mind. So this equation can be turned into eigenvalue equation, right? Do you see how? So you could have done like omega squared uv is equal to something over here, uv, right? And then you have c over m1 times minus 2u minus 2. Do you agree with this? Yes? Then you have c over m1 times 1 plus e to the minus ika. I hope you agree with this too. m2 1 plus e to the ika minus 2c over m2, etc. Right? So I know how boring it has become for you, so I will just Phonon dispersion of diatomic chain. So this after you solve this equation, you know, you can imagine how to solve this, right? Do you want me to write down the equation, the relevant equation? Hmm? It would be nice. So basically, we are talking about an eigenvalue equation. So omega squares will go here, right? So basically, you have to solve minus 2c over m1 minus omega squared c over m1 1 plus e to the minus ika then c over m2 1 plus e to the ika minus 2c over m2 minus omega squared, right? And then you have to take the determinant and set it to 0, right? So if you do this, you get something like this: m1 m2 omega to the 4 minus 2c m1 m2 omega squared plus 2c squared 1 minus cosine ka. At some point, these I to the ka's magically disappear, okay? Because they become some sum, okay? So then what happens is that you get this. How many modes do you expect to get? Any ideas?
3. 6.
Okay, how many atoms do you have? 2. How many degrees of freedom? 1. They are moving only in one direction.
But don't you have like separate for both of them?
Hmm?
The degree of freedom for one is not.
No, if okay.
Don't you add?
Okay, how many degrees of freedom do you have? Then your answer is 2. Right?
Yeah.
Yes. You're right.
What was your answer?
I was asking how many degrees of freedom each one has. So like 2 times 1. It's the same thing. Okay. So 2 degrees of freedom in total in the system. How many modes? 2 modes. Okay. So 2 modes, and you can see its picture here. So I forgot to mention something, and now I see that. Okay, you remember we had something like this, and I said after this point there is no meaning, pi over a, but this also has some meaning. This is what physicists call first Brillouin zone. Okay, have you ever heard of it? Okay, it's a nice book. You can read first few pages of it by Charles Kittle. You will get all these concepts that I don't have time to teach. But what about the next one? So if you can see that you have two modes here. One of them is called acoustic, the other one is optic. So basically you will get 2 branches from here, and in one of them U and V will be 1 1, okay? In the other one, which will correspond to translation, right? In the other one, U and V will have opposite signs. Maybe not 1 minus 1, but something related to M1 and M2. So actually, let me cheat from here. I think it will be something like minus M2 plus M1. Okay? So basically, one of them, this mode, is a superimposing of a wave on top of this movement. Do you understand? But this one, this other one, which we call optical mode, optical branch, will correspond to waves that are propagated by this kind of motion. So just multiply this one with a wave on top of it. Okay, does it make sense? Yes? And notice that as lambda goes to infinity, as k goes to 0 and lambda goes to infinity, you are going to multiply this one with a constant, right? And this would still have a restoring force. Do you agree with this? Or not? Just imagine a chain, and each M1 you move to the right, each M2 you move to the left. Right, left, right, left. So you are basically doing this to the crystal. There will be a restoring force, right? That's why you have this finite omega at k equals 0. And this one corresponds to translation. And this is called acoustic because that's the way sound waves are traveled, right? Actually, in fact, this slope will correspond to sound velocity in that chain. This slope. Okay? Do you have any questions so far? Any questions? Like it could be, okay.
I think if the atoms were allowed to move in 3 directions, we'd have a total of 6 modes.
6 modes. And how many acoustic branches?
3.
3 acoustic branches, right? And 3 optical. Yes, very good. Why do we call optical branches optical? Because they can interact with light. Okay, because when you move these atoms like that, you introduce polarization, which is a nice way of interacting with light. Okay, so I always show you like papers with more than 1,000 citations, right? Okay, let me show you another one, and this time it's mine. I want to talk to you about this paper and how these very concepts were used in this paper. Okay, if you will allow me, is that okay? So back in 2009 or 8, you have heard about graphene, right? This honeycomb structure of carbon atoms, very has amazing properties, etc. So our question was, can it be made out of silicon? Because in periodic table they appear right at the bottom of each other, and maybe from germanium. But the problem is carbon likes all hybridizations, sp1, sp2, sp3. All of them are almost equally likely for carbon. That's why it's an element of life, right? Because it has all these different bondings, richness. But silicon usually prefers sp3. So thinking that silicon can make this flat honeycomb structure was madness back in the time. Nobody would agree with you. And there was a point. So let me tell you what we did. We used the same thing as we used here, like calculating phonons. But phonons are also good for understanding stability of materials. Why? Because let's say you plot. Let's say somebody brought you this plot of phonons, okay, and asks you whether this material is stable or not. Okay, what is your answer?
Stable.
It is stable. Why?
Because omega is positive.
Exactly. Omega is positive everywhere. That is relevant.
So there's a restoring force.
There is a restoring force for any kind of displacement in the atoms, right? So let me show you a plot from a book I wrote with my friends, of course. Yes, this is the plot. And you can see that if you calculate phonons of planar silicene, like take the carbon atoms, get them out, and replace them with silicon, and do these nice calculations, do you see the mode that goes to negative? It's actually going to imaginary. And you are not seeing just the fact that it's imaginary, so there's no restoring force. You also know what's the problem with the structure, because you can look at the mode and it will tell you that one silicon atom wants to go up, the other one wants to go down. Okay. By the way, maybe I haven't mentioned, this structure has 2 atoms in the unit cell, and if you repeat this, you will get like the honeycomb structure. So how many modes are you expecting? From the whole thing in 3D. 6, right? 2 atoms, 3 degrees of freedom for each one. 6. you can see that you have actually 6 branches here. Okay, 1, 2, 3, 4, 5, 6. And this one, the optical out of plane mode is negative. But if you allow the system to go that way, if you allow one atom to go up and another one to go down, then you will get a stable structure. You get a stable structure. Okay? This was it. And in 2012, this structure was actually synthesized on top of silver surfaces. And then you remember that we also predicted germanium counterpart, like germanene. That was also synthesized in 2014, I guess, on gold substrates. So basically, what I'm trying to tell you today, with the closing remarks, that with calculating vibrational properties of materials, plotting the phonons, you can discover a lot about the material itself. For example, let me tell you something. You can see that these ones are linear, right? And you know the sound velocity from there. But this one is quadratic. Do you see? It goes quadratic. Actually, if you fit it to a quadratic polynomial, okay, from the fit you can derive the bending rigidity of the material. So how rigid it is against bending. So you can discover a lot of material properties doing vibrational analysis, like Phonon calculations, and you can also discover new kind of materials, okay, in a computer. Okay, let's stop here. Thank you all for coming.